Hello my energetic students. Today I will start with a module in which there is a lot of energy involved. But before I start the module, let me tell you one thing. In this module you will be studying the present situation and prequel. So there is current movie going on and there is a prequel also. So let's understand. The very first concept, origin of hydrogen spectrum. Origin of hydrogen spectrum. What is spectrum? Let me tell you. There is a nice incandescent bulb which is glowing, and there is this Fresnel's prism. So from this light, it is bending and everything is taking place through the prism, and it's falling, and it is giving rise to a continuous spectrum, just like a rainbow, which you see, which we have learned. Big deal. But now this photons or the energy particles, when they are passed through cloud of cooler gases and then they are passed through prism, what really happens is you get such kind of spectrum. You will be asking, sir, what is that? Absorption. It's a cooler gas. So what the cooler gas does is it takes some energy. Heat always transfers from hot body to cold body. So the energy is lost. And if the energy is lost on the screen, what you can see is no energy. If there is no energy, that's why at certain points you can see black lines. But compared to this, it's a continuous rainbow. Now, if you pass the excited gas, I would say hotter gas, when that is passed through the prism, what you'll get is an emission spectrum. Because the hotter gas, when it cools down, it releases the energy. Now, this energy is released according to Bohr's third postulate. It is given in terms of discrete particles. And these discrete particles are nothing but your spectral lines. This is the phenomena which Rutherford wasn't able to explain. So the whole picture got cleared. That is continuous spectrum, that is absorption spectrum, this is emission spectrum. Simpler as you get. Who is continuous? That is continuous. Who are discontinuous? One and this second. And to explain the whole idea, this is once again the complete picture. And to explain the experimental setup, I have one more picture for all of you. Super beautifully done. And why that slits are there? So that you can get some defined lines and so on and so forth. I'm pretty much sure it's very clear. Now, emission spectrum of hydrogen atom. There is one more experimental display to show you. Why am I showing you so many lines? So that you can understand the gravity of situation, that this is the most important topic and the most amazing one. So dear students, emission spectrum we have discrete line. In absorption spectrum again we have discrete line, but they are thicker lines. So did you see where there is a gap in the second diagram? That gap is shown by the light in the first diagram. And when there is a light, there is no light in the first diagram. Simple and easy. Spectrum of hydrogen gas. Consider an atom of hydrogen, one proton, one electron, okay, having in the innermost orbit. Now what I do is I provide this gas with some energy in terms of heat. Electron accepts the heat. Oh, delicious heat. I love it. And once electron gets excited, it jumps into the higher orbit. Now that is called absorption. Mind it, that's what cooler gas did. But then electron stays for a lesser time, 10 raised to minus 8 seconds, and it comes down. It comes down and then the energy is again liberated. And this energy is in terms of photon, bundle, quanta. If suppose it gets de-excited to the next orbit, you get another type of photon with much more frequency. So these are the EM waves of different wavelength or different frequencies. These electromagnetic waves are called as electro characteristic? No. Only characteristic spectrum of hydrogen gas. Why I took the pause was, the reason was very simple. Electromagnetic waves are now shown as particles. But these particles are characteristic of that atom. That's why they are called as characteristic spectrum. So proceeding forward, there was, I told you there's a prequel about this man. Amazing person. This so-called Balmer, there's a speciality about him. Even he saw the same thing in the year 1885. He observed it, very nice, beautiful, I'm just loving the whole idea. Beautiful. But after observing, he measured the wavelengths. See, he was so precise about everything. And then he named the 4 lines as H alpha, H beta, H gamma, H delta. Why H? Because of hydrogen. Alpha, beta, gamma because they were in series. Then he measured the wavelengths also. And their wavelengths were, please remember this, 6563 Armstrong, H alpha. H beta was 4861 Armstrong. H gamma was 4341. And H delta was 4102. And that's what hydrogen spectrum, all 4 lines are. He could see these lines. That's why all these lines comes into visible spectrum, whose 4 lines values are given as follows. Remember it, note it, practice it. He played with these numbers because they didn't have any other work, just like Bohr did, which is second postulate. So after playing, what he did was, he came up with a new formula. He told, ladies and gentlemen, and whosoever it may concern, 1 by lambda is equal to R, I don't know what R is, 1 upon 2 square minus 1 upon n square. Where lambda was wavelength, of course, n was your so-called orbit number. But then when people ask, what is R? What is 2? Illa. So he wasn't answering, he was just pondering. I don't know because I don't know. I just calculated it and got it. Same like Bohr. And he couldn't answer the mystery which was then solved by Bohr by giving the 3 postulate. Thank you, Bohr, but even you have your drawback, remember? So that's the entire idea of Balmer's hypothesis. So through this we understand how spectral lines came into place and what kind of hypothesis Balmer took in place. Thank you.